Okay.
Okay. Hello, everybody. Welcome again to the European Non-Associative Algebra seminar. It's a pleasure to introduce the speaker of today, Professor Leandro Vendramin from the Vrije Universiteit of Brussels. The title of his talk is Nichols Algebras over solvable groups. Please, Leandro.
Thank you. Thank you all for being here and for the invitation. So the plan is to give some sort of overview on the classification problem of Nichols algebras and give a kind of a new result explaining what happens in the case of solvable groups. Okay. So first of all, I need to give some kind of very basic definitions. Okay, sorry. Okay. Yeah. We will start with a braided vector space. What is a braided vector space? Well, it will be a vector space together with a linear map, bijective linear map from V tensor V into V tensor V that satisfies the braid equation, which is this formula that I put there. So it is called the braid equation because, well, the picture somehow resembles a braid, right? So we will say that C is a braiding. This is also known as the Yang-Baxter equation or the quantum Yang-Baxter equation, depending on the author somehow. But I will try to use the terminology of the braid equation and braidings. So you start with this. So let me give you some examples. So the first super basic example is some sort of deformation of the flip map. So you take a vector space, finite dimensional, say, with basis x1, x2, and so on. And then what you are going to do is to flip every pair of basis vectors. So you send xy tensor xj to xj tensor xy. And you can also twist this a little bit with every non-zero constant. And, well, you will have a braiding in this case. These are known as braidings of diagonal type. So the only requirement that you need to put on the scalars Qij is that, well, they need to be non-zero because you want this map C to be inverted. But then there is no other condition on this bunch of scalars, okay? This example is extremely important. It is kind of very deeply connected with the theory of quantum groups. And, well, you can generalize this example into some other direction. And this is the direction I'm interested in. So which is the generalization? Well, you fix a group and then you take any subset of G, which is invariant under conjugation. And then you form the vector space with basis in this union of conjugative classes of G. And then what you do is essentially conjugation. So conjugation will give you a braiding. And again, as we did before, you can twist this conjugation with some non-zero scalars. But now things are not so good as before. It's not that every collection of non-zero scalars will give you a braiding, right? This will not happen. You need some conditions on this QXY to have a braiding, to still have a braiding. If they are all equal to 1, for example, well, that's fine. This is a solution. But not every collection of scalars will work. In fact, this Qij, for them to work, what you need is that there is some condition which pretty much look like a cocycle condition, a two cocycle condition. And in fact, well, they need to be a two cocycle of X, where you understand X as a quandle, and this is a cocycle of the quandle X, okay? This is not so important for us, so I will not go into details. But this family of braidings is very, very important for me and for this talk. This, of course, includes those of diagonal type that I presented in the previous slide. But, you will see that this is kind of very, very rich. So these braidings are known as braidings of group type, okay? Or you could also say conjugation braidings, why not? Okay? So, very good. So what is the point? Well, we need to know. So the idea is that you will start with this solution, with this braiding, and then you will produce an algebra. But to explain you how this definition works, well, we need to recall what can you do with these braided vector spaces. And one thing that you can do is to represent the braid group or braid groups, okay? So what is the braid group? It's a group that has this presentation. So you have n-1 generators. And relations. So the relations are essentially the braid relation. If two strands are, together, say, and then, well, if they are really separated, then they commute. Okay, these strands. So, and the point is that every braided vector space will produce a representation of the braid group where in V tensor V tensor V tensor V n times, where V is the underlying vector space of the braided vector space. Okay, so essentially what you are doing is just to replace the generator sigma I by the braiding Ci. Okay, this produces a representation of the braid group precisely because you are asking this map C to satisfy the braid relation. Okay, so you can see this very, in very concrete terms, say that n is equal to 4, and then the braiding will be just this diagram that I put there. And then which are C1 and C2? Well, you have n equals 4, so you have 4 strands, and then C1 is to braid the first two, and C2 is to braid the second with the third. Okay, so and these are the pictures, and what I'm doing is just to represent with pictures what is happening in the braid group. Well, this is precisely the representation that I constructed before with C. Okay, it's exactly this. Very good. Now, as I said before, every braided vector space will produce an algebra, which is called the Nichols algebra of the braided vector space. It's a kind of a very rich object. I will give you just the definition of an algebra, but we will, if you go into this theory, you will see that there is much more to study, right? This is a very, very deep object somehow. It has way more structure. It's not just an algebra. Okay, so which is the definition? Well, this is a kind of a crazy definition, but very concrete. So here you see that you can really play with your own hands with these algebras, but also immediately you understand why these objects are so hard to study, right? So what are you gonna do? Well, the Nichols algebra will be given as a quotient, a certain quotient of the tensor algebra. It will be a graded algebra over non-negative integers. In degree 0, you will have your field. In degree 1, you will have B, the braided vector space B. And then you will have a quotient of V tensor V tensor V tensor V, depending on the degree. And what is what you have to divide? What is what is what you are doing in every degree n? Well, you divide V tensor V n times by the kernel of some linear map. And this linear map is the quantum symmetrizer. What is this guy? Well, the first quantum symmetrizer that you will see there is sigma 2, which is identity plus C. This is a map that goes to V tensor V to V tensor V. The next one will be, well, you need to divide V tensor V tensor V, V tensor V tensor V by the kernel of sigma 3. What is sigma 3? Well, it's this expression that I wrote there, right? So maybe you can recognize what I'm doing. So essentially what I'm doing is to run over all the elements, sum over all the elements of the symmetric group S3, and then instead of using elementary transposition, well, I just replace the elementary transposition, but by the representation I can produce with the braiding, with the C, okay? So instead of using the elementary transposition 1, 2, I'm using C1. Instead of using the elementary transposition 2, 3, I'm using C2. And these are all the elements of the symmetric group S3. That is why I have 6 terms. And then you can continue with this, but of course, this is kind of a bit crazy, right? Because the next one will have 24 terms and so on, but you have this recursive formula that you see there, which allows you to compute all quantum symmetrizers in principle, right? But here is very clear which is the problem with this definition. It's very concrete. You can very easily put this into a computer to compute these kernels of the symmetrizer up to some degree n. But of course, you cannot do this for all n, right? Because this grows really, really fast and in a crazy way. So very quickly, you end up not knowing what happens in degree n for some big n, right? And this is kind of very hard because it's hard to understand the structure of these algebras because, well, this definition doesn't look to be, good enough in some sense. There are other equivalent definitions, but more or less the problem is everywhere, right? You don't know what happens in degree n when n is big, right? And there is kind of not easy to guess what could happen there. When you can, well, this is kind of a theorem in general, okay? Good, so some well-known examples of Nichols algebras. Well, the first one is the symmetric algebra, right? The braiding there is just the flip. And this is a very nice example of a Nichols algebra. And the other example, very nice also, is, well, if you take V and minus the flip, then you get the exterior algebra. The first one, as you know, is infinite dimensional. The second one is finite dimensional of dimension 2 to the dimension of, okay? And these objects, well, you can imagine that they are quite important because, well, these two examples are examples of Nichols algebras, right? They are known in physics as Fock spaces, and they were rediscovered several times in pure math, also in mathematical physics, by Nichols, doing Hopf algebras by Voronovich, doing differential calculus on quantum groups, by Lustig, doing, again, quantum groups, by Majid, doing some sort of non-commutative physics, and so on, right? They appear quite a lot of times with maybe a different definition, but they are quite important, okay? Good. So what is the problem I want to discuss? I want to discuss the classification of finite dimensional Nichols algebras, okay? Why? Well, because it happens, this is kind of a consequence of the lifting method of Andruskiewitsch and Schneider, that these Nichols algebras are very, very important for understanding Hopf algebras or quantum groups, small quantum groups, or in general pointed Hopf algebras, okay? So, good. So, because of that, what I want to do is to classify finite dimensional Nichols algebras coming from groups. What does it mean? Well, it means that my braided vector spaces are those coming from these braided vector spaces of group type. Okay? So just to put a better kind of framework, well, these braided vector spaces of group type are just Jeter-Drinfeld modules over a group algebra. Okay, so you fix a group. A Jeter-Drinfeld module V over G is going to be, or K of G if you want, is going to be a G-graded G module. So you have an action of G, and also you have a gradient given by G, and then you have a compatibility, these two structures, and which is the compatibility that if you act with G on the H component, then you end up in the component GH G inverse. Okay, so these are this is the compatibility. So these Jeter-Drinfeld modules are kind of very important in the theory of Hopf algebras. They form a very nice category, so you can tensor them, and then you still have a Jeter-Drinfeld module. So they form a tensor category, also a very nice tensor category, but also it's braided, meaning that every time you have a Jeter-Drinfeld module, then this guy is automatically a braided vector space. And the braiding is given by this. Okay, so this more or less tells you that these Jeter-Drinfeld modules, or these braided vector spaces, are kind of the same guys that I presented at the beginning, these braidings or braided vector spaces of group type. Okay, good. So this is the state of the art of related to or regarding the problem I mentioned. So you have braided vector spaces, say of group type, then you can split this into two. You have diagonal type, which corresponds to the case where the groups are abelian, and this was solved in characteristic 0, and there are several results in characteristic P, and also there are a lot of applications to Hopf algebras, to the theory of Nichols algebras, to mathematical physics, a lot of very, very interesting application. I will not talk about this. I will talk about the non-abelian case. So in that case, you have non-diagonal type braidings, so your groups are non-abelian, and then you can split the problem into, again, two cases. So your objects, your Jeter-Drinfeld module, could be either indecomposable or decomposable, whatever that means, right? Like you cannot split this into some, say, of smaller objects. Well, the decomposable case is also completely solved, and the indecomposable case is open in full generality, but there are a lot of results, and I will present a very recent result, which, doesn't finish the problem, but, well, it's kind of an achievement, I would say, right? Because we are getting close. Good. So, okay, this is, as I said, this is, I'm recalling the definition of a diagonal type is when the group is abelian. So I told you that in characteristic 0, the problem was solved. Okay, the problem was solved by Heckenberger. Then Ivan and Hionov found generators and relations for all the Nichols algebras. There are very, very important applications to Hopf algebras, especially a classification result of Andruskiewicz and Schneider, which can be understood as some sort of axiomatic way of presenting small quantum groups. And then there are also very interesting applications to physics. This is kind of not my domain, but there is a paper there are several papers of Semikatov and also a very interesting paper of Simon Lettner, where they use Nichols algebras to do some physics, okay? Again, I will not talk about this. I just wanted to mention this to put, somehow all of this into context. I would like to discuss more what is happening in the non-diagonal case. So why we care? Well, one possibility would be because, well, this kind of part of the theory is relevant in some other areas. Like, for example, in combinatorial Schubert calculus, in kind of a combinatorial algebraic geometry, these objects also appear, okay? And they also appear, of course, in this kind of more general theory of quantum groups, or if you want to be more picky with the language, in the theory of pointed Hopf algebras with a non-abelian corradical. This would be some sort of family of say, non-abelian type small quantum groups, if you want, okay? Okay, so as I said before, you can split the problem into two, right? So your braided vector space could be indecomposable or decomposable. So what does it mean? Well, I will give I will give you the definition and I will explain what this means. Okay, for decomposable, the problem was completely solved and the solution is kind of very nice. So it all starts with a very old result of Matthias Grania, where that says that if the square of the braiding is the identity, which means that, you apply the braiding twice and it's the same as doing nothing, then the Nichols algebra of a direct sum is just the tensor product of the Nichols algebra, okay? So this is, this is, say, as graded vector spaces or even vector spaces. So if you are interested in the classification of finite dimensional one, well, clearly, if you want to be in the composable case, well, you need the square of the braiding to be different from the identity, right? Otherwise, considering sums like this one that I have here is exactly the same as doing a tensor product of two guys from the composable case, right? So to be in the decomposable case, and this is why I was using the quotation marks, well, you need this extra assumption, right? Like the square of the braiding is different from the identity, okay? So it's not just a sum as a vector space, what you want to study, but you need this extra condition to be like really in the outside the case where you have essentially one component, right? Sometimes you could use the braided in the composable or braided decomposable, but I didn't want to make the terminology too heavy, okay? Good. So now, a technical definition, you have a yet a dreamful module, which is a graded module by G. So, well, you can consider the support. What is the support? Is the set of elements such that elements of the group such that the G homogeneous component is different from Z, okay? It happens because of the definitions that this guy will be a union of conjugacy classes of G, okay? I will need this definition. So, and the theorem that we proved with Heckenberger some years ago, well, maybe around 10 years ago, is that, well, we solved the case, the decomposable case, where you have only two summas. So the theorem is like this. So suppose that you have a non-abelian group G, and then you have two absolutely reducible yet dreamful modules over G. So absolutely irreducible is because we have no assumption on the field, right? So if you just put, say, characteristic 0, the complex numbers, if you put the complex number, then you just put irreducible there, okay? This is just a technicality to make this as general as possible. Assume that G is generated by the support of B and W. So essentially, I mean, you just take the G, the smallest G you need to realize your Jetta-Drinfeld module B plus W, okay? Assume, of course, that the square of the bragging is not the identity. So you want to be in the decomposable case. You want this B plus W to be a real decomposable guy, okay? And of course, then you assume that the Nichols algebra of B plus W is finite dimensional. Then what we proved is that you kind of know what is happening with G. So namely, well, G will be either a quotient of some extension, some very nice central extension of SL23, which is the group of 2 by 2 matrices with determinant 1 and coefficients in the field with 3 elements, or a quotient of a central extension of a very small dihedral group. And when I say certain, it's because I know precisely which type of central extensions, right? I can give you a very precise and nice presentation of the groups that appear in this theorem. I'm just writing this like this to make it less technical, okay? So, yeah, and the theorem, of course, is just the beginning, right? It's the tip of the iceberg, because with this theorem, then you kind of know everything that is going on. So, for example, you can recover precisely the structure of V and the structure of W, and you can also compute the dimensions of the Nichols algebras appearing in the theorem, okay? So you know everything, okay? So, yeah, here is, for example, how the theorem looks with all the extra information in over the complex numbers. So you have a non-abelian group, then you have your 2 irreducible Jetta-Drinfeld modules over the complex group algebra of G. Again, you assume that G is generated by the support of B plus W. Again, you assume that the square of the braiding is not the identity, and also that the Nichols algebra of B plus W is finite dimensional. Then I know exactly which Nichols algebras can appear. And here you have the table, right? So V plus W will have dimension 4, 5, or 6, and the Nichols algebra will have dimension one of the numbers that you see in the table, okay? Good. So this kind of settles completely the degree, sorry, the rank 2 case when you have 2 summits. The theorem that we have, of course, is for every field, not only for complex numbers, but the list of possible algebras is a bit longer. That is why I just put for over the complex number to make it a bit simpler, okay? And in case you want to see how things look, well, here I have an example. You remember that I said that one possibility is to have a quotient of a central extension of SL23. Well, this central extension is the group T. So you will have 5 generators, X1, X2, X3, X4, and Z. Z will be a central element. And then the relations between the X are given there. So these are the relations. Just take a look, like deeply, sorry. If you take a look at this, you will quickly recognize that these are conjugation relations, right? So for example, if you do X1, X2, X1 inverse is X4. If you do X4, X1, X4 inverse is X2, and so on, right? Yes, this is the group. Then you take any quotient of the group T, and you can see how your modules V and W look like. So they will depend on parameters. These parameters are given by characters of centralizers of your group. So rho will be the character of G, because it's the centralizer of the central element. B will be a non-zero element of degree Z, then B will be the basis of your B, and the action is given like this by some representation of G. Sorry, it's a degree 1 representation, okay? And what about W? Well, for W, you need to compute the centralizer of X1 in G, which is the group generated by X1, X2, X3, and the central element Z. You take a character of that group, which is -1 on X1 and 1 on X2, X3, and it's a kind of free in principle in Z. And then you take an element, non-zero element of degree X1 in W, And then you form a basis of W, which is 4-dimensional. And then, well, here you have the table of the module W, right? So the elements of the groups, the generators of the group x1, x2, x3, x4, and z are acting more or less by -1 in all the W's, and z is acting, they are acting by -1, but also permuting the basis elements, right? And the z, the central element, is acting by a parameter, okay, by a scalar, and this scalar is the sigma of z. And in this case, well, what you get, so if you want to have a finite dimensional, you have some conditions on these parameters that you have, so these need to be satisfied, and then you get a very big Nichols algebra, which is the one that I gave you there, okay? I mean, this looks a bit technical, but I'm just showing you how the theorem really works, right? Because it's a bit more than just this statement that sketchy statement that I put at the beginning, okay? So, and this happens for all the examples, a very precise description of all the modules, and in terms of the quotient of the group that you get, okay? Good. And as I said before, right, it's very nice that the theorem holds for arbitrary characteristic, not only for characteristic 0, because this will be relevant later, okay? So this is the full list of algebras that we found. So again, V plus W could be only 4, 5, or 6, but then you see that you have several other dimensions that can appear. So, you know, kind of weird things happen in small characteristics. So you have extra examples in small characteristics, okay? Good. And what happens if I have more than 2 summands? If I have at least 3, finitely many, but at least 3? Well, again, you need to have this kind of good notion of decomposable, which is easy in this case, right? Because the sum of all the modules should not admit a decomposition into 2, where with the square of the braiding between these 2 components equal to the identity. Okay, this is kind of a natural way of extending the result to more than 2 summands. But then, yes, as you can imagine, right? If we are going to have a lot of summands, then, well, you need a way of describing the groups and the modules. But this is not so easy as what you could do in the case of 2 summands, right? So you need to, I mean, in principle, in theory, you could, of course, describe very precisely the groups and the modules. And this is crazy, right? Because it's a lot of works and a lot of pages, and no one wants to read a theorem with a statement of 10 pages, right? So what you do, or what we did, was to put this into a graph, okay? The graph is called skeleton. And what is a skeleton? Well, it will be a Dinkin diagram of finite type with a bit of extra information, right? So the idea is to put the structure of the Jeter-Greenfeld modules into a Dinkin diagram, or into a diagram. But it happens, which I find quite surprising, is that in the end, you will get a finite dimensional Nichols algebra if your Dinkin diagram is a finite type. So for example, if you are in the ADE case, which as you can expect is the better case, the less exceptional case, well, these are the diagrams that you will find. So you see that they are kind of a classical Dinkin diagrams, with the only difference that you see 2 points at every vertex instead of only 1, right? Why is that? Well, this is because the dimension of every component will be 2, okay? And then, of course, in some weird characteristic or in some exceptional examples, you will have something more, right? Like you will have diagrams of type B, which are a bit weird, like B3 prime, beta 3 prime, and beta 3 double prime. Or you will have this type C, type F4, with some extra labels, because, well, this is something that you need if you want to recover the structure of the module, okay? How the theorem looks like? Well, the theorem is now very easy. So it's suppose that you have at least 3 components. Again, you have a non-abelian group G, and you have this tuple of absolutely reducible Jeter-Greenfeld modules over the group algebra of G. Then the Nichols algebra will be finite dimensional if and only if you can attach to M a skeleton of finite type. So this Dinkin diagram of finite type. And once you have this Dinkin diagram, you have a dictionary that allows you to recover the structure of the module with all possible details. Okay, but everything is somehow hidden and codified in just a Dynkin diagram. And what it happens is that if you have 3 summands, well, it's a bit exceptional, and the diagrams could have extra labels or something. But as soon as you let the number of components, the number of summands grow, things tend to be less exceptional. And so if the number of summands is big enough, say, and you are over the complex number, this is quite nice because it's not really exceptional, I would say. So degree rank 2 summands was very, very exceptional somehow. Rank 3 summands is also a bit exceptional, especially if you are gonna allow characteristic P positive characteristic. But if you are over the complex numbers and with a big number of summands, this is essentially a Dynkin type classification, which is very good. So this solves completely the problem in the case of decomposable Jeter-Drinfeld module. Okay. As before, of course, you can get the dimensions, and here you have the dimensions that you will find in type AD in the less exceptional case. Okay, so you see that these are the numbers. Good. But what about the indecomposable case, right? Like because in general you do the other way around, right? You start with the problem, then you say, okay, let's split the problem into 2, either the pieces that the building blocks, the pieces that I cannot decompose further, and then once I know this, I can know everything. With Nichols Algebras seems to be the other way around, which is a bit weird, no? So what happens in the indecomposable case? Well, there are some results and some conjectures that are kind of interesting. So these results are pretty old, are from 2010. But suppose that you have an alternating simple group, and you have a non-zero Jeter-Drinfeld module over this group, over the complex number. Then all the Nichols algebras will be infinite dimensional, right? And something quite similar can be proved for sporadic simple groups, at least for all of them, but 3. So there are 3 exceptions for the theorem where we don't know what is happening, but in all the others, we could prove the same result, that there are no finite dimensional Nichols algebras over that group. Okay, good. So this kind of, first of all, it's very clear, which is how you should continue with this problem. You should try to see what happens with other simple groups, right? So first of all, we don't know what happens with these 3 examples, Fisher 22, Baby Monster, and Monster. These 3 sporadic simple groups, we don't know. This is kind of an open problem. And what happens with other simple groups, right? Like simple groups of Lie type. This was done, not completely, right? But there are a lot of results of Andruskiewicz, Carnovale, and Gaston Garcia. They did a lot of work on this, and they have some families of simple groups of Lie types without finite dimensional Nichols algebra. So the conjecture is more or less clear, right? So if you have a finite simple group and you have a non-zero complex Jeter-Drinfeld module over that group, then the Nichols algebra will be infinite dimensional. We don't know if this is true, but we believe that this is true. Okay? This is something that, this is one thing that is going on in the composability. Another thing that is going on, and I think that this is the problem in this research area, is what happened with the symmetric, right? So take n bigger or equal than 6 and take a Jeter-Drinfeld module over or complex Jeter-Drinfeld module over the symmetric group. Is this guy finite dimensional or not? Well, of course, there are some partial results, right? Essentially, we know more or less everything, but there is one case that is open. And this case that is open is that of Fomin-Kirillov algebras, which were algebras that appear in the 90s in a completely different setting to try to understand combinatorial Schubert calculus, okay? To try to understand the cohomology ring of the flag manifold in combinatorial terms. Not at all related with Hopf algebras or quantum groups, at all, okay? So So which is the problem that is still open? Okay, so of course, if you want to study Nichols algebras over the symmetric group, you need to parse all conjugacy classes of the symmetric group and then try to see what happens there. The case that is open is the case of transposition. Okay, so let's say that n is bigger or equal than 3 now. Xn is the conjugacy class of transpositions in the symmetric group. You take the vector space, complex vector space with basis in these transpositions, and the conjugation braiding with a -1 as a scale. Okay, this is something. When this guy is going to be infinite dimension? Well, it is finite dimensional if n is 3, 4, or 5. And well, n equals 3 you can do by hand because it's very small. For n equals 4 and 5, you need computers. You need to use first non-commutative Grodner basis, and then the structure of a bit more the structure of these algebras to try to understand what is going on, right? So, but we don't know what happens when n is 6. And this is an open problem from the 90s, right? We don't know if these algebras are infinite dimensional. We don't even know if these algebras are quadratic. We know that for n equals 3, 4, and 5, these algebras are quadratic, but it is not clear what is happening for n bigger or equal than 6. Okay? So this is one open problem that is very, very important. And kind of if you can solve this, very likely you can finish the classification of now. You could finish the classification of Nichols algebra, I think. Okay, but which examples do we know, right? Apart from these 3 that I showed you. So this is the full list of example of indecomposable non-abelian, say, examples that we know. So the dimension of B could be 3, 4, 6, 7, 5, or 10. And these are the algebras that you know. There are some repetitions. This is not a typo. These are different algebras that you can find. And this is the full list for all characteristics. Okay. So this is the full list of indecomposable examples that we know over a non-abelian. Okay. And we kind of believe that this is the full list, that there are no other examples. But at the moment, we couldn't prove this. Okay. So yeah, this is a very natural question. Is this list complete or not? We don't know. I think it is, but of course, it's just a bet. Okay. So recently, with Heckenberger and Udi, we proved the following theorem. So we proved that the list is complete if the dimension of B is a prime number. So the theorem in characteristic 0, right? The theorem looks like this. Suppose that G is a non-abelian group, and B is an irreducible complex yet a dreamful module of G with a prime dimension. Of course, we are going to assume that the support of B generates G. So this G is precisely what you need to realize your set. Then the Nichols algebra is finite dimensional if and only if, well, your algebra is one of the algebras of the table with prime dimension B. Where the dimension of B is a prime number. And this prime number cannot be anything, can be 3, 5, or 7, and these are the only algebras that you can, and that's okay. This is interesting because it solves some problems that were there, right? Like I mean, I'm not saying this, but this is solving several problems that, you know, were important, right? Like, for example, what happens if you have a very particular type of a braided vector space of indecomposable type, right? Very particular with the braiding given by some formula, some calculation, like an Alexander quantum, for example, over a field or over something like this. Well, this kind of solves some problems that were there. Okay, so it's saying a lot more than what you see in this webpage, and also the techniques that were used here were new and very powerful, right? And then we started working with Andruskiewicz and Heckenberger to try to see how far we can go with this. And yeah, we recently proved the following theorem. essentially what we did was to solve the classification problem of Nichols algebras over the complex numbers for all solvable groups. Okay, so this, of course, I mean, the symmetric group, which is the one that I told you before, it's not solvable, right? So this guy is still there, giving us hope, but this kind of really is a big achievement, I think. So the theorem it goes like this. So you have a solvable group, non-cyclic. Why non-cyclic? Well, because with the settings that we put here, if you put cyclic, then you will go to the diagonal case that was already solved, right? So that's why you put non-cyclic. This is not really an assumption somehow, but okay. So you have a non-cyclic solvable group, and you have a Jeter-Drinfeld module V over the complex group algebra of G. Again, you are going to assume that the support of V generates G. And then if the dimension of your Nichols algebra is finite, then, well, essentially, you know which kind of Nichols algebras will appear. And all the algebras that can appear are known and are those that are there. So essentially, it's the full table with the exception of that one that can be realized over the symmetric group S5, which is the only non-solvable example that we have. Okay, so this was it's a preprint at the moment, but this really solves several open problems that were around, right? Like very particular braidings that people used to think that we're gonna give a finite dimensional algebra because I don't know the dimensions of the homogeneous components were growing in a very slow way or something. Well, all of these guys are given infinite dimensional Nichols algebra. Okay, yeah, and again, this list of this small list of algebras is very precise, right? Because these are the examples that were known from several years ago, maybe from the 90s or early. Okay, and just to finish, I will give you an application that we also have in this paper, is that what you can this theorem on Nichols algebras has a natural application to the theory of Hopf algebras. So essentially, combining the lifting method of Andruskiewicz and Schneider with the theorem, you get some sort of Fay-Thompson theorem for pointed Hopf algebras. If you don't know much what I'm saying, like if you don't know what a pointed Hopf algebra is, well, let's say that we are giving some sort of Fay-Thompson-like theorem for finite dimensional quantum groups. Okay, and what is a Fay-Thompson-like theorem? Well, like if you have odd order or odd dimension of this finite dimensional quantum group, then, well, you kind of know what you are dealing with. Okay. So, well, I think this is the end of my talk. So thank you very much.
Okay. Thanks, Leandro, for your interesting talk. Are there any questions? Comments or remarks? Okay, I cannot see any questions. In this case, let's thank the speaker again. And we resume on next Monday at the usual time.
Thank you
very much.
Bye-bye.
Bye-bye.